This is going to be sample problems 10.8 through 10.13. So we're going to jump right in. They want us to calculate the molar mass of a gas, and it says a large evacuated flask initially has a mass of 134.567 grams. When the flask is filled with a gas of unknown molar mass to a pressure of 735 torrs at 31 degrees Celsius, the mass is 137.456 grams. When the flask is evacuated again and then filled with water at 31 degrees Celsius, its mass is 1,067.9 grams. The density of water at this temperature is 0.997 grams per milliliter. So assuming the ideal gas equation applies, calculate the molar mass of the gas. Our first step is to figure out what the mass of that gas is alone. So we're going to take the mass of the gas and the flask and subtract the mass of the flask. And so that's what they did here, 137.456 grams, which was the mass of the flask and the gas. Subtracting just the flask of 134.567 grams gives you the mass of just the gas at 2.889 grams. The second thing that we want to do is figure out what the mass of the water is, and that's because the water can't be compressed. So if the water's volume, if we can figure out the water's volume using density equals mass divided by volume, then we know the volume of that gas as well. So we need to figure out the mass of the water. They give us the density, and then eventually we'd be able to solve for the volume. So we take the 1,067.9 grams, subtract the mass of the flask, which is 134.567, to get the mass of the water being 933.3 grams. So remember, density equals mass divided by volume. So if we solve for volume, we're going to get mass divided by density. So we're going to take the mass of the water, 933.3, divided by the density of water, 0.997, to get the volume of the water, which is going to be 936 milliliters, which is the same as saying 0.936 liters. And the reason we do this is, again, because the water can't be compressed. So that volume of water is the same then as the volume of the container, which then means the volume of the gas. So on the next slide, we're going to continue. All right. So now we know the mass of the gas, we know the volume, which means we can calculate the density. So we're going to take mass divided by volume, which is the 2.889 divided by 0.936 to get 3.09 grams per liter. And what they're ultimately asking for is what the molar mass is. So using that equation, we know that the molar mass will equal the density times the gas constant times temperature divided by P. We would need to first convert the, because they give it to us in torrs, the 735 torrs into atmospheres by dividing by 760, because 760 torrs equals 1 atmosphere. And they give us 35 degrees Celsius, which means we have to put it in Kelvin, so we're going to add 273. And when you do that, you will get, where's my temperature, 304 kelvins and 0.09671 atmospheres. So then you can plug all those numbers in. So taking the density of the gas that we calculated up here, the gas constant, the temperature that we just calculated, and the pressure that we just calculated to get 79.7 grams per mole. So that is the molar mass. All right, example number 9 is relating a gas volume to the amount of another substance in a reaction. So this is basically taking what we're given to then figure out something different about the equation. It says automobile airbags are inflated by nitrogen gas generated from the rapid decomposition of sodium azide, which is NaN3. So the equation is 2 moles of NaN3 solid will decompose into 2 moles of Na solid plus 3 moles of N2 gas. If an airbag has a volume of 36 liters and is to be filled with nitrogen gas at 1.15 atmospheres and 26.0 degrees Celsius, how many grams of NaN3 must be decomposed? So our first step is to use that gas data to figure out the number of moles of N2 I need to make. And then once I figure out the number of moles, I can do my stoichiometry, work backwards to figure out the moles of NaN3, and then eventually convert that into grams of NaN3. So here we know that the number of moles using the ideal gas equation is going to equal pressure times volume over the gas constant times temperature. So thankfully they've given us atmospheres this time, but we do still have to convert Celsius into Kelvin. So you're going to take that 26, add 273 degrees or 273 Kelvin to get 299 Kelvin. So then you can plug in all the other numbers, the 1.15 atmospheres times the 36 liters, and then divide the gas constant times 299 to get 1.69 moles of N2. Here comes the stoichiometry. Now, if you were in class with me, we'd be doing this in like one big long equation on the top instead of separating it into these two, but either one works. 1.69 moles of N2 using the molar ratio from the balanced equation here. You're going to see that for every 3 moles of N2, I need 2 moles of NaN3. So that's where this 3 and the 2 came from. And because N2 is what we're working with, it needs to be canceled out. So it goes on the bottom. The NaN3 is what we're looking for. So it goes on the top, which means I'm going to multiply my 1.69 times 2, then divide by 3 to get 1.12 moles of NaN3. Now I need to convert that into grams, so I'm going to take my, 22.99 plus 14.01 times 3 to get a total of 65.0 grams, and that's how much 1 mole of NaN3 weighs. So you take your 1.12 moles of NaN3, multiply it by the grams we just got to get a total of 73 grams of NaN3. Alrighty, page. Example problem 10.10, here we go. A mixture of 6.00 grams of oxygen gas and 9.00 grams of CH4 is placed into a 15.0 liter vessel at 0 degrees Celsius. What is the partial pressure of each gas and what is the total volume of that vessel? So our first step is to convert from the grams that we have into moles, and then we're going to use that moles in the ideal gas equation to figure out the pressure of each one separately, and then you can add them together to get the total pressure. So starting with oxygen, we've got 6.00 grams O2. We know that oxygen is 16 grams per mole, but we've got 2 oxygens, so 16 plus 16 is 32. We're going to take the 6, divide it by 32 to get 0.188 moles of O2. Do the exact same thing with CH4, except in this case, we're going to use the molar mass of CH4, which is 16. So 1 for each H and 12 for the carbon. And we're going to take 9 divided by 16 to get 0.563 moles of CH4. Then the next step is to use the ideal gas equation, so PV equals nRT. But we want to solve for just P. So you're going to divide V over, and you're going to get P equals nRT over V. Now the N, because we're looking for the partial pressures of each one, you're going to use just the N of oxygen first, and then just the number of moles of the CH4 second. So you're going to take the 0.188 moles of O2 times the gas constant, 0.08206, times my temperature. So again, they give it to us in Celsius, but luckily 0 plus 273 happens to be 273. And then you're going to divide by the volume, which is 15 liters. So the partial pressure of O2 is 0.281 atmospheres. You're going to do the same thing with the methane, the CH4, except we're going to take the 0.563 instead of the moles of oxygen. So now we're using the moles of methane. Multiply by the gas constant, multiply by the temperature, divide by the volume, and get 0.841 atmospheres. So those are the separate partial pressures. And then it wants to know what the total pressure is in that vessel. And all you have to do is take the partial pressures and add them together, which gives us a total of 0.281 plus 0.841 to give us 1.122 atmospheres. Here's another practice problem you guys can see and work on. Alrighty. Number 11, relating mole fractions and partial pressures. So a study of the effects of certain gases on plant growth requires a synthetic atmosphere composed of 1.5 mole percent CO2, 18.0 mole percent O2, and 80.5 mole percent AR. So calculate the partial pressure of O2 in the mixture if the total pressure of the atmosphere is 745 torrs. And then part B is, if this atmosphere is to be held in a 121 liter space at 295 K, how many moles of O2 are needed? So we want to convert first. Did they give us moles? 18%. Oh yeah, okay, so you just want to, since it's a percentage, it's 18%, you just want to convert that into just moles. So you can divide by 100 to get 0.18 moles of O2. So that's the mole fraction. And then since we know the total and we know the fraction, all you have to do is multiply them together. Oh, they do it right here. Okay. So 0.18 times the total pressure of 745 torrs to get 134 torrs. And that would be the partial pressure of oxygen, which is our first part. So part B then is where we need to figure out how much oxygen, how many moles of oxygen would be needed if we were going to use a 121 liter volume and 295 kelvins. So you can use that ideal gas equation to figure out, to solve for N. So N equals P times volume divided by RT. So then all you have to do is plug in our amounts here. But first we have to convert from the 134 torrs into atmospheres by dividing by 760 torrs. So that gives you 0.176 atmospheres, which is going to go here for pressure. The 121 goes on top for volume, gas constant, temperature. So remember, multiply first, then divide, and we're going to get 0.879 moles of oxygen. Okay, I don't have enough time to go over anymore, so I'm going to stop it here and then post the next two in another shorter video.